Welcome back to another CADSIM Plus tutorial. My name is Renaud Denzer, and today we will be covering another cycling related example to try and answer questions such as how much power is needed to ride a bike at a certain speed and inclination, as well as how fast will I go if I can only expend 200 watts of effort. Now, I've picked a cycling related example because it's something we might all understand and it's not too focused on engineering work, and at the same time I'm going to provide you with some new knowledge on how to use CADSIM, and here's essentially what we're going to cover in this tutorial. I'm going to outline our learning objectives. So the first thing we'll cover is signal lines. The second thing we're going to talk about is to create tables with variables and specify them, as well as format them. I'd like to discuss linking CADSIM Plus via DDE client with variables to and from an external application. In this case, that would be Excel. I'll discuss the optimizer module, the controller track module to do some control of a free variable, and the noise module. So I will go through these topics while giving an example about bikes. So a couple of days ago, I landed on this website here, which is a calculator created by Bagna here, and there are a bunch of references to calculate cycling wattage. So for example, here there are these formulas that are referred to, and some losses due to lubrication and chains and whatnot. And so in entering my body weight, the mass of my gear and bike, the speed I'm riding at, and adding a slope, an inclination, I can find out the wattage that the rider has to expend to go that speed, which turns out to be 534 watts. Now what I've done is I've created an Excel sheet using these formulas here, and I will put the links to this calculator in the description, and I ultimately get the same power for entering these same coefficients and variables used in the calculator. Now my idea is to send a slope from CADSIM into here, do a bit of a calculation, and send it back to CADSIM, and to use CADSIM to do these calculations that you see here. I want to use CADSIM links to internally come to these numbers. And so here's my canvas of CADSIM. Oops. Here we are. This is the one. Let's zoom out a bit here, and here are these equations that were in that reference moments ago. And the first thing I want to do is create some signal lines. Now, by default in CADSIM, if I start drawing a process line, it's going to draw a blue line, which is a process line, and we don't want that. We want to create signal lines. So I'll go into my default graphics attribute setting and select as the standard part in here. It's the lines, the piping lines. I'm going to select signal logic because that's what we're working with here. So that when I'm going to draw a signal line, I get the defaults of the signal line. So let's give this a name. I'm going to add a process text to that line. I'm going to call it the speed. Might as well give it a units in kilometers per hour, seeing as signal lines don't have units. And we're going to add a format to this signal line. We're going to create a new one, put a number followed by a period and 2 numbers to get 2 sig figs, and drop it on that line. So when I press run, it'll ask me to save the drawing and specify. Here I'm going to add a direct setting and say we're traveling at 30 kilometers an hour. And so when we run, we see 30 kilometers an hour here. We see it in the dialog box here. And I want to create the same thing for the slope. So let's highlight what we just drew, click the copy button, select let's go back one step, I did too fast. Select the point of origin and click finish, so that when we paste it, I see my new signal line. Let's edit the name and call it the slope and units percentage. We'll go to the multi-spec, edit it, and select a slope of 5 degrees. And if we run that, it should be satisfied with what we did. And when we hit run, we see our 5 in that signal line and 30 over here. So this was signal lines. Let's create some tables with variables and specify them. So how do we do that? I'm going to draw a polygon. So select the draw polygon tool, click and drag across my screen to size a table, and we'll give it a name called table of coefficients and variables. And the first thing we're going to do is add a process text inside that polygon. So add text to polygon, and we'll call that the G for gravitational acceleration in meters per second squared. Now I'd like to see that S as the square, so I can click here to square the 2. You'll see it gets squared. However, I don't want to square the bracket, so I go back down, and there you go, you get your meters per second squared. Not to forget, we want to create a variable, so it's not just a name, it's a variable. And so when we click run, it'll ask us to specify the value. Let's do that. Let's click run, and as expected, it wants me to specify this free variable along that polygon, along that table. Let's select this spot right here, and we're going to call it 9.81 meters per second squared. We do want to make a save change. Now before I hit run, I want to add a format. Let's create a new one. It wants me to select the polygon for the format. Let's go with number to significant figures, so number, period, number, and there's a drop down menu if there were more than one. Click OK and drop it here. I'm satisfied with that. Let's press play and run, and there you have it. We see our value. Now as you can see, for these equations to calculate the cycling wattage, there's quite a few of them, quite a few things that I've already prepared ahead of time. So I am going to delete this and just import or copy from an existing drawing. Now this is something you can do as long as the two drawings are in the same folder. You can copy from one drawing and then paste it into another. Let's select this destination. There we go. Now let's just delete this so we can specify in a moment. So here we got our gravitational acceleration that I did earlier, along with a couple of more things. In fact, I have within my table, I have a calculation for this variable here, which is the total mass of the rider plus the equipment. And how was this specified? Well, it used a linear spec. As you can see, there's a little L here. Let's go visualize what it looks like. It is the addition of this guy here plus this guy here to give the total, which should be the sum of these two. Similarly, it's going to ask me to specify this last remaining spec here. So let's press run, save the drawing, and there it goes. It shows up as a free variable that needs the specification, because keep in mind, this is a variable and it doesn't have a specification yet. So this is a linear specification as well. Say I were to select a multi-spec and a linear equation, there's going to be a little problem. It's only going to allow me to add one other specification, namely, well, whichever one I select. In this case, the first one is the wind speed. But I cannot add a second term. In order to be able to do that, let's re-choose this specification and use the local specification or equation, linear equation. And that will enable me to select not just the wind speed from the drop-down menu here, but I can also add another term. In this case, we want the speed v, which was the speed of the rider. And so, and that was the 30 kilometers an hour that we created earlier. Now, there we have it. Now, we have to be consistent here, because to be able to calculate these forces and the resulting power, we have to do a unit analysis, and it requires meters per second, not kilometers per hour. So let's convert that to meters per second by multiplying with a factor of 0.027, which is 1,000 meters per kilometer divided by 3,600 seconds per hour, and that's that factor of 0.27. So if I click finish, it's happy with the specification. Let's press run, and there you have it. We see all our specified values. I weigh 77 kilos, my bike is 11, total mass. Here's the friction loss. Now if I wanted to change any of them, I can select 5, bring it back to 4.5. My total speed is 8.3. Let's say I added a bit of wind here, negative wind. It slows me down. Let's go back to 0. Let's just say it's a calm day. All right, so this is how we specify and create tables. And now we can move on to the calculation of these equations. So once more, we're going to use some signal lines. So I'm going to create one here, and I'm going to create one for every calculation that needs to be done. So it's going to ask me to specify them sequentially. Actually, you know what? Change of plans. Let's just start with one, because as you can see, the first one has a bit of math here that involves using the arctans and the sines. Now, although CADSIM does have a parts library with signal math that includes, for instance, the cosine. I think I just skipped it here, the cosine or the sine. These aren't just about all you need for engineering problems, but we don't have a module for the arc sine or arc cosine. And I thought this was a great opportunity here to push the value of the slope into Excel, get Excel to calculate it and bring it back. So this would be this here, DDE client with variables to and from Excel. So let's do that. Let's do a bit of this. I am going to yeah, let's get rid of the signal first, and we'll go into my insert. No, pardon me. This would be tools, create a dynamic data exchange axis. Let's do this right here. Let's pick a spot, click and drag across the screen, and we will call it calculations in Excel. And you'll see automatically it adds the DDE client, and it will automatically detect which applications are open on my desktop. And I'm interested in working with the sheet power.xlsx, and I'm going to say OK. Now it's going to ask me to create some variables, and let's call this one the slope, and we are going to give the slope to the external. That's why the direction is pointing this way from CADSIM to the external app. And we're going to call this one sine arc tan slope, and the other one we're going to call cosine or cos arc tan slope. So it's going to look for these variable descriptors in this Excel file in order to be able to communicate. So I got one guy that I'm sending over to to Excel, and then it's going to calculate something with these two variables and send it back to CADSIM. So I'm satisfied with this. I'm just going to hit OK, and there we have it. Now I got to go over to Excel, and I've already pre-highlighted these guys because I wanted to do something with them. So I could have entered, let's go back to the help file. I could have entered, which one is it? It's this guy here. Let's go to the help files. Let's click module help. I could have entered, for example, row 1, cell 1. So it would have written, instead of slope over here in the bracket, it would have written out row 1, cell 1, or I gave it a name. So let's do that instead. Let's give the cell a name in Excel. And how do you do that? So I click the cell, I right click it, and I go define name, and I'm going to call it slope. Click OK. So when I click a cell, instead of D12, here we have slope, and there's my list of named cells. I'm going to do the same thing with these two guys here. Let's define the name, and I'm going to call it sine arc tan. I believe that's what I named it. It has to match. It has to match. Sine arc tan slope. Sine arc tan slope. Okay. And this guy here, right click, define name, we're going to call it cos arc tan slope. Beauty. Now if I look at the calculation, what is the calculation? Well, it's going to pull the value that CADSIM is sending to Excel into this cell, divided by 100, and evaluate the arctan of that, followed by the sine of that. Similarly here, arctan of the slope divided by 100, followed by the cosine of that expression. There you have it. If I change this to, say, 10, you can see these values change, the wattage changes. We were familiar with, what, 534 with a slope of 5 degrees, and so these are the calculated values. Let's click Save, and we go back to our drawing. And I think this should satisfy it. Let's press Run, say Run. Right, it needs to specify that what is it going to send to Excel? Well, the slope. It's asking for the slope, and I'm going to give it a equate to another variable. Select the slope, add a term, which is a slope here. So it's going to pull that signal. Perfect. And it's happy with that. And so when I press Run, that 5 gets sent to Excel, and it receives the information from Excel, the calculated variables back. Let's go see. Here we go. You can see it's kind of flashing because it's updating every so often. Let's push a different value of slope. Let's go back to that 10, and we should see different values of sine and arc. Now, I don't remember what we initially saw, but one we can do quickly is chart, and we chart all three, say OK. All right, so maybe let's go to 5 here, apply. There you go. There's some difference here for the calculated variables. Let's exit that. So now we have essentially out of this calculation here box, we've got this expression taken care of. Meaning, if I'm trying to draw a process line, a signal line to represent f of g, let's see here, this is, I'm going to press Run. It's going to ask me to specify this guy. I am going to utilize the specification to calculate that. And as you see, there's 1, 2, 3 terms that are needed. So I'm going to use a multi-spec, and I'm going to use, pardon me, I'm going to use a, because I have several terms, I'm going to use the local specification and select product. As you might have seen it, I cannot select product, it's grayed out, if it's a multi-spec. So let's go and select a product, because it's a product of 1, 2, 3 terms. And let's drop it here, add a term. The first term I want to add is the G, so I'm going to pull out the G here. I'm going to add another term, which is the slope, and I'm going to get that from sine arc tan slope, sine arc tan slope. And the last term is the total mass, which is over here. I could put that spec anywhere, but it's nice to kind of line it up with the table. And here I can select whatever I want, and I do want to get the total mass. And if I click Run, I get an answer. It's 43.09. Okay, is this right? Is this what we calculated here? 43.09. Perfect. So it's doing the same thing as Excel. Alright, now I have a couple more equations. Might as well run them one by one. Let's do them all. Why not? We can skip to the other parts in the description, or you can move fast forward ahead. So there's a new one here, a new line here, and a new line here. All of these guys essentially, well, there's actually going to be a fifth one to represent that last one. Let's deal with these three new ones first. Okay, it's asking me to specify the bottom one, so let's go 1, 2, 3, 4, 1, 2, 3, 4. All right, it's this is a bad idea because, well, let's try it anyways. It wants me to create this addition, this sum, and in order to sum, I'm going to use a linear equation and add this term, add a term, this term, add a term, this term. So it's this guy plus this guy plus this guy. It'll be FG, FR, FA. Finish. Actually, it wasn't mad about that, so that's good. Secondly, it's asking me to specify the third equation, which will be the aerodynamic drag. And for this guy, I think we're also going to use a product. So let's do it here. It's kind of messy. Well, let's do it here anyways. Add term. So let's skip the 0.5 for now. Let's go straight to CD. Let's pick up CD, aerodynamic drag, which is this guy here. Add a term. We need rho, which is the density of air. Rho. Add a term. We want this term, which is the total speed, the net speed. Here is what I called it. And it's squared, so might as well take the opportunity to add the square here. And everything is multiplied by 0.5. I think I'll be happy with that. And the last one is FR. So another product. Let's put it here. Add a term. It's G. Gravitational acceleration multiplied by the cosine arctan. Add a term times the mass, the total mass. Add term times CR, which is the coefficient of CR. What was it again? I forget. Ask me to save. Let's go look at it in my Excel. CR. Rolling resistance. CR. Rolling resistance. Which was 0.005 because we had slick tires on asphalt. That's where how that was selected. All right. Let's clean this up a bit. Actually, it's already running. I forgot to kind of put these guys on a snap. If they're superimposed, they should line up perfectly, and then you should be able to see what they are. And I thought that was kind of messy that I picked this guy over here. Let's make it equal to accelerate, more decent. And the last one is also a product. So it's going to multiply the sum of the forces times the loss factor times the speed. So let's press play. Let's select a product and add a first term. The first term is the power. Well, I guess this is, I just realized this shouldn't be called power just yet. This should be the sum of the forces. But it was this guy here. I'm going to add a term and multiply it by v, which is the speed that you're traveling at over here, and divide it by the loss factor, which was a side calculation done here. So this guy represents 1 minus loss over 100, 1 minus loss 100. But it has to be a division, so to the -1. And again, to satisfy the units, we're working in meters per second, so I have to convert the speed over here. I believe that's what that's for. Let's press play and see what we get as a result. Okay, we get 51. 13, 40. These look all right. This guy is not what I expected. Let's see what's. I have another drawing to the side there to compare with. Oh, of course, because when I added the last guy, I used gravitational acceleration. It was meant to be actually the loss factor. So that's where I made a mistake. And let's press play. I think we were expecting 534. Press play. There it is, 534. So we went through that whole ordeal. Maybe we'll skip forward to the next learning objective, but you get the gist of how to specify signal lines using mathematical expressions, or actually using the specification wizard. Let's double check here on our learning objectives, which goes into a discussion about using an optimizer. Okay, yeah, so our calculation here will tell us our loss. Let's add a format. Our power, it will give us our power for cycling at a certain slope at a certain speed. So I can change this to 25 kilometers per hour. I expect there to be less power needed. Correct. At 30 kilometers an hour, if you are going at a less steep incline, you will require less power. Yes. Say you were a cyclist and you can only manage to expend 200 watts of power at any given time. That means you won't be able to sustain that speed. You will have to slow down in order to not expend over 200. So we're going to try and use the optimizer module to do that. So this is an introduction to how to use the optimizer module. So let's go into draw mode, and I am going to change the polygon attribute to become a logic equipment. Okay, so that when I draw a polygon, instead of giving me a blue table like this, it's going to give me a signal logic type polygon. And I'm going to use the keyword optim for optimizer. And I'm not entirely sure if CADSIM has acknowledged it is an optimizer module, and one way to check that is to go click module help, and if this shows up, then we're in the clear. If it goes to the default module, then that means it hasn't acknowledged that this is a optimization module. We go in the help files in module parameters, and we can use any of these 4 names for CADSIM to recognize this polygon as an optimization module. So it worked, and I am going to make use of the number of coordinates, which is a unit keyword, which is mandatory and it's needed. So I'm going to type in num coordinates equals to 1, because I'm only interested in changing one thing. So let's go into the process text inside that polygon and type num coordinates equals 1. Let's not forget it needs to be unit cast. And when I hit run, it's going to ask me to specify some stuff. So let's do that. It wants the optimized variable, and we know that that's going to be the watts. And so I'm going to do an equate to another variable and equate it to the watts. Click finish. It asks if we want to use annealing. For now, I'm going to say, oh, I didn't want to do that. I wanted to do a direct 0 setting. I don't want to use annealing. Finish. The estimated dead time, I believe that has to do with how long does it take for this to be solved? How many iterations does it need to get the answer before I can do something? And in my testing, I determined that that needed to be a 2. We can read more on that in the help files. And fractional convergence I have set as 1. And here are our min and max coordinates. So our min coordinate, we're going to say the slowest we can go is 1 kilometer an hour. If we go 0, we tip over and fall. So let's go at least 1 kilometer an hour. And the maximum we could possibly go, probably on a decline, let's say it's 50, because we will break or something because we're too scared. Free variable signal, let's see, show. It's asking me to delete that. Let's delete it for now. I'm not sure why it's asking me to delete these things. It's unhappy with something. So let's can't return. Let's not abide to this. I'm not entirely sure why it didn't appreciate that. We had a direct setting here. We said it was 30. And we said our slope was 5. Let's put those back. I'm not sure why it complained. Anyways, we're back in business. So it's up to the user to define how to use the optimizer module. Let's go to the help files. And first thing I wanted to mention was the dead time here. The dead time is the optimizing you ahead of the rest of the units and with the rest of the units in calculation order, even without apparent dead time if the units are not in ideal execution orders. Oh, we weren't in steady state. We're in dynamic simulations. It's set to the time it takes for the dependent variables to stabilize after a change in the independent variables. And one way we can enhance that is by trying to use the order of execution. So it does the calculations faster. And this is for now not really important. I think the reason why I wanted to click this is I wanted to show what annealing was. And annealing basically allows the simplex to, once it thinks it's converged at some point, to zoom out again and try looking over a landscape. Here it is. So a good analogy to understand this process, the process of annealing, is to consider the simplex as a bird overlooking a landscape with many hills and valleys of different heights and depth, respectively. With a standard simplex, the bird is initially not at a sufficiently high altitude, which corresponds to a bad set of initial points. Then it cannot see the hills surrounding it. And so there could be a deeper valley somewhere, but it doesn't get to see it. So annealing gives the bird energy to go high enough to get a global overview of the landscape. But we're not using annealing for now. What we do want to do, though, is specify our speed as what we will change with the optimizer. So I deleted that spec, and I am going to select and equate. So I'm going to equate my speed to the current convergent. I think that's what it is. Let me double check with my sample. I have current coordinate. This is what I selected. Let's press. Actually, it's up to the user again to specify we want it. Right now, we're just pointing at the power, but we want to set some boundaries of the boundary of this power output, which we said we wanted to limit to 200. And so to do that, I am going to add a signal line and a part called the absolute value. So it's going to be the absolute value of a calculation. And you'll see as I specify it, I'm going to go press run. It's going to ask me to specify this guy. I will use a linear equation. I'm going to say make this guy equal to my power minus 200. So it's going to minimize, the optimizer is going to minimize this difference, this power. So let's try to find 0 so that it's equal to 200, because my signal, my desired signal of 200 minus 200 is 0, and optimizer wants to find that valley. And I am going to select this equate and bring it down here. So instead of equating it to the power, I want it to equate it to what I put in as a boundary, which is the power minus 200. So 200 is my desired outcome. Minus 200 would be 0, and it tries to get to that 0. So let's see how it performs. So it's trying a bunch of stuff here. It's getting closer to 200. Oh, there it is. It's already found it. So we were able to find the speed at which we will expend 200 watts for a slope of 5 degrees. Let's increase that slope to 10. I think what is happening right now, it's not resetting this here. I think I have to exit the drawing and select a different slope. So there it is. So now it starts off with what I believe is to be 10. Let's run it now. And now the slope is 10. It wants to know the speed at which it'll run, it'll expend 200 watts. And it is 7.5 kilometers an hour. Anyway, this was nice, but it wasn't very efficient, because when you're trying to get to a target set point, you would normally use a controller which has integral action that continues to try and narrow the gap to the set point. And unfortunately, what we're doing this exercise using an optimizer, and the path to get there is destructive. So you wouldn't want to operate in a process that random in a random scattered way, but instead using a controller, you'll get a much smoother approach. So let's do that. Let's try replacing this optimizer with a controller. And to do that, I'm just going to delete this guy here and its specifications, and we're going to instead place a controller. So I'm going to go to the parts library, insert part. I'm going to select a process part, look for controller. In the options, I'm going to select a track controller. And press OK. Let's position it where we want. And we'll call it speed. Why not? And let's press run. See how it's asking us to specify here. Alright, it wants us to specify the speed. Now we want the controller to tell us what the speed is. So we're going to use an equate. And I'm going to equate my signal to the current output of the controller, which should be the current, which will be the current ratio, because we're using a track controller, so it's going to move according to a ratio based on a master variable. So the measure variable for this controller is going to be our power, which is down here. That's right, let's finish that. And our master variable is going to be the slope. So it's gonna keep an eye on the slope and use a ratio to help the controller track where the slope is at to arrive at our desired set point, which should be 200. So let's go and edit. Yes, I do want to save that. Let's go back to draw mode. in our controller, there's a specification here. Let's move this guy around. Let's tilt it to 90 degrees and edit the specification of that track controller and enter our set point as 200. And we shall see how this guy behaves momentarily. Let's press run and play. And it's doing some work. Let's see what's happening. Presently, it's whacking back and forth. So let's put it in manual, and we will control manually to our set point, see what that current output should be. So we're close. And then if we go to settings and we use auto tune from here on out and click run, so we're tuning the controller. So here's the response for a bump test. The current output is in red, the present value is in blue, and it fits a model through here. Let's go click next. Let's run this guy and find out how good it's tuning. It seems to be relatively nice. It's a bit jaggedy, so we can use lambda tuning to try and smooth it out a bit. Let's use 5 here. We get slightly smoother approach. I think we're happy with that, so let's click finish. So I got some new tuning parameters here. And if I go back to automatic mode and press run, it shall find the speed at which we're getting 200 watts of output for this inclination. And if I were to change the incline to 5, that controller should fairly quickly get to the new speed because it uses the track controller and the ratios. So it's sort of finding it. Seems a bit slow here. Let's try to tune at a more realistic slope. I know a slope of 5 degrees is quite high. This is just a schematic. These are the actual slope, 18, but that's nearly impossible to climb as a cyclist. But 2.5 is a slope. So let's tune this guy around that 2.5 set point. Click next, run, and we'll keep those parameters the way they are, even though they're jaggedy. We just wanted to go there quickly. And so it should, with small variation, be able to track the new speed to expend 200 watts fairly quickly. There it is. Fairly quickly. Now, this brings us to the last part of our learning objectives, is to use the noise module. So let's have a little bit of fun with that. Let's see what the noise module does first. Now that we've tuned the controller, I'm going to go and select, first I'm going to draw a little process line, find the part, the logic, and noise. Oh, it's in the math module instead. Okay, and out of it comes another signal line. And it's going to ask me to specify some stuff. Starting with, let's say, the base case, the base slope. Let's take 2.5%. And now it's asking me to specify the overall standard deviation. So how much overall standard deviation will this noise module give on the output from the input? Let's say 10, that's the default. And the noise standard, let's see what it asks as a default, 1. Okay, so we create a noise module. So it's going to take a value, add some noise to it. Now let's chart that noise. And in fact, let's track it together. Let's add another stream, which is the input. So there should be 2 lines, one in blue showing the noise and one in red showing the signal, which is 2.5. So let's press run here. So this is how much our signal output is differing from the input due to these deviations, standard deviations. So let's reduce the noise a little bit to have a more smoother curve, I guess, random curve. Let's see, starting now when I click OK, it's not as jaggedy, and it's fairly, as you can see, the standard deviation is quite high. So maybe that's a bit high because we want to get a signal to correspond to slope. So let's bring it down to earth a little bit. Let's pick 1. So it should be closer to the input by an overall standard deviation of 1. And what does this start resembling? It starts to resemble, say, a path, or let's say a natural road. And so my idea now is to use this controller for our speed controller, where our slope is now not specified here by the user, but we're going to replace that and make it and equate to the noise. And so what this does is we're going to have a path that's going to show different slopes. That slope is going to be sent to Excel. Excel over here is going to take that slope that's going to change and calculate the arcsine and arctans, and spit those results back into CADSIM to calculate the power, which is going to be controlled using the speed. So let's just see how that works out. So it's going to try its best using the track controller to maintain this at a roughly 200 watts effort from the rider in this journey over here. And this is the speed at which the rider would be going at. And that was our noise module. So to recap, once again, we showed how to create signal lines, how to copy stuff. We showed and covered how to create tables that you can add variables to specify and format. Subsequently, we also were able to communicate to Excel, send to Excel a value to receive a calculation and bring it back to CADSIM. We use signal and the specification to do calculations, to calculate, in this instance I haven't labeled them, but in the same order as they are outlined here, the force of gravity, of friction, and aerodynamic drag, to give a total force used in the calculation of power, and with taken into account a loss due to friction. For fun, let's change here the constant for drag. Let's go look again in over here what kind of drag we would get on gravel or let's see if we're writing on sand, 0.03. Let's do that. Let's add 0.03. See how much slower we are going to go. Much slower for the same amount of effort because we're writing on sand all of a sudden. So that was an example of calculation using signal lines. We presented the optimizer module. You'll have to go back in the video to check that out because we since replaced it with a track controller. And lastly but not least, we added the noise module to show you how that works, how you can create some noise to a signal. Thanks for joining me during this long journey. We're happy to receive some feedback for the next video. And if you have any questions, please write a comment or write to us at mail@oralsystems.com. Please like and subscribe. Go to our LinkedIn page to see some more examples, and we'll catch up soon. Thank you.